All right, so this is day 14 in Unit 2. Got a homework you'll upload on the assignment as a single PDF. And we're going to talk about the chain rule today. So you should have already turned in your area function packet that you've been working on for several classes. So the first thing we're going to look at today is graphing on the Inspire accumulation functions. So the function you worked with in the area function packet, this equation is roughly one that would match that. So we worked with it from 1 to 7. So if you want to put that in, you have to use the piecewise function template. So notice it's selected the 2-part piecewise function template, and all you do is you put it in the top version and then you delete it out. Um, and then what we're going to do is we're going to graph our accumulation function, and because it will have been an F1, we can just do the accumulation function from 1 to x of F1 and then have t and dt. So for this one, I've already put that graph in. So now we can graph the accumulation function. So your integral template. Now, I think on mine it's in the second row, but on your guys it's in the third row. So we're doing the integral from 1 to x. And our graph of the original function was an F1. If you hit the variable button that's above the 9, you should be able to select F1, or you can just type in F1. And then we've got to make sure we do a different variable than the x. Okay, so that is important. That variable always has to be different. And if we hit enter, so maybe make that 8 so we can see a little more. So if we hit enter, we've now got our accumulation function. I'm going to move that accumulation function out of the way. So some things to notice are that the maximum, the relative maximum of the accumulation function is the same as the 0 of the original function f1. And the reason for that is, think of under the blue function, you're adding positive area, you're adding positive area, you're adding positive area. And then at that value where that 0 is, then we start adding negative area. So we have accumulated less because we've now started tacking on negative area. Also notice the relative max and mins of in the blue function, the function we were finding the area underneath, matches the inflection points of our accumulation function. Because at that maximum in the blue, that's where we are, the instant we're adding on the most area. So that's where our slope is going to be the greatest. And then although it's still going up, we're not adding quite as much because our blue graph is not quite as high. So that's a few things to notice with that. So we're going to practice together putting in one all the way. So if you go to the second page of the day 14 notes, so it should say BC 2-14. So we're going to see if we can graph the accumulation function of sine t from 0 to t, and we're doing it on 0 to 2 pi. So the first thing that we've got to do is we've got to go to our piecewise function 2-part template. Oops, I lost mine. So now in mine, notice I'm putting it in F3. Oops, I did it again. And that's just important to note when we go to do the accumulation function. So we can delete out the second one, so we only have one part. So we're just going to have sine x and we're going to go from 0 to 2 pi, as you see on the top of the second page of the notes. So we'll go 0. Our inequalities, you got to do control and equals if you're unsure of that. And then we'll have our 2 pi. And there's our original function. I'll drag my label out of the way. So now note it's an F3 So we're going to now graph our accumulation function. So you can hit Tab or Control G to get up a graphing line. We'll select our integral. We are going from 0 to x. And if I go to variable, I'll now go out and select F3 because that's where we put our graph, and make sure you use something different than x. Okay, so hopefully you're practicing that on yours as we're doing it here. So here is our accumulation function in pink. So again, notice the 0 of the function we were finding the area underneath corresponds to a relative extrema in the accumulation function, a relative max in this case, because it switched from positive to negative. Notice the max and min in the function in F3, the function we were finding the area underneath, corresponded to the inflection points on our accumulation function. So just a couple interesting things to note, and also just to show you how you can get an accumulation function on your calculator. Okay, so going to the notes, the bottom of the second page, we're going to look at the chain rule and integration today. So just a review of the chain rule. So if you take a derivative of a composition of a function, so a function inside of a function, you take the derivative of the outside part, keeping the inside the same, and then you do times the derivative of the inside. So if we wanted to do the derivative of that first line in purple, we'd do our power rule, we'd bring the 5 out front, keep the inside the same, but then we'd have to multiply by the derivative of the inside, so times 3x squared. Well, what if we wanted to work backwards? So what I'm going to do is I'm going to take that 5 that's a constant and put it out front. We would have x cubed minus 4 to the 4th times 3x squared. And then in the integral, we always have to have that dx there. Well, what I want you to recognize is that this is just the derivative of what our inside function was. And that's the general idea of what we're trying to get to happen when we want to do an antiderivative involving chain rule. Usually what you do is what's called U substitution. You can use any letter, but U is the most common one done. We're basically going to do a change of variable. And what you do is whatever's your inside function, you let that be your U. So we're going to let U equal x cubed minus 4. Well, we're now going to take the derivative of U with respect to x. So that would be du over dx equals 3x squared. Get the du by itself, and that's 3x squared dx. So that's essentially a differential. And if you remember way back when we first did integrals, I mentioned why do we have that dx there? Well, it's because it's part of the differential. So what we're going to do is we're going to do a replacement. We still have the 5 out front. X cubed minus 4 we just defined as u. So that's now going to become u to the 4th. And the entire 3x squared dx now becomes our du. Well, notice what that gives us is a simple integral in terms of u's now. It needs to be in terms of a single variable. You can't have a mixture of x's and u's. Well, now let's just do our antiderivative for u's. So we'd have the 5, but then we'd have 1/5 u to the 5th plus c. If we neaten this up, this is just u to the 5th plus c. And your final step is you re-sub back in for u. So you replace the u with what it was equal to. So we get x cubed minus 4 to the 5th plus c. So that matches with what we had originally up above, just we had the plus c case where it was plus 0 technically. So we would do this anytime it's not one of our basic integration rules, or if we notice there's a function inside of a function. Basically, chain rule would have been applied to get that derivative, so we have to do our u substitution in order to integrate and undo that chain rule. So if we look at the next page in the notes, here's our general rule. So this ends up being our du eventually, and this ends up being our u. So we get a function in terms of u only that we are then able to do the antiderivative. Now, when deciding what to be u, you can look for it in one of two ways. What's a function that's inside another function? Or what's something that we're used to seeing as a plain old x? And if it was a plain old x, we could do an antiderivative rule. Well, in this first example, the inside function would be the 5 plus x squared. Now, we would technically do du over dx and then multiply the dx over. We're going to do so many of these that I am okay if you automatically just bring that dx over. So eventually we'd have du over dx, and we would have equals 2x. But because the dx we know is going to swing over, I'm okay if you just jump right to the fact that du is equal to 2x dx. That step will save you a lot of time in the long run. Well, let's see if we're matched up. 2x dx, that's going to become du. And then the inside here is going to be our u. So now we'll have the integral, we'll have square root of u times du. And that's something we can work with, because that's really just u to the 1/2. So the antiderivative will be u to the 3/2 with a 2/3 out front, and then plus c. And then this will give us 2/3, and we'll fill back in for our u. Our u is just 5 plus x squared. Now, you can always check by doing your derivative. 3/2 times 2/3 is 1. We'll have the 5 plus x squared to the 1/2. That matches our square root. And then times the derivative of the inside, which would be 2x. That matches. And then the plus c, its derivative would just be 0. So that would go away. All right, next one. Our function that's inside a function would be the x squared plus 3x, because that's a thing that is being cubed. So we'll let u equal that. So our du would just equal 2x plus 3 with the dx on the end. So this is going to become our du, and this inside is going to be the u. So now we'll just have the integral of u cubed du. And for the antiderivative, exponent goes up 1. Divide by that exponent out front. Don't forget your plus c. And then we'll just replace our u. So we got 1/4 x squared plus 3x to the 4th plus c. So your u substitution takes a tricky integral and turns it into something that's manageable. And the next one, our function inside the function is the part inside the cubed root. So we'll let u equal 6 plus 2 sine x. Our derivative, the du, will be 2 cos x dx. So this is our du, and that part inside is going to be our u. So this becomes the integral of cubed root of u du. Or, in other words, that's u to the 1/3 du. So our new exponent will be 4/3, because adding 1 is like adding 3/3. So out front, we'll divide by 4/3, which is the same as having a 3/4. And then we need our plus c. To finish off, we'll have 3/4 times our u, which was 6 plus 2 sine x, to the 4/3 plus c. Now, two words of warning of common errors I see with these. Number one is people will forget to sub back in for the u and they'll stop here. That's one common error. The other common error is when people go to sub in the u, they forget to put the exponent back on what u is being raised to. So just keep an eye out for those two things. They come up quite a bit. All right, our last page of notes for today. What if you don't have a perfect match? In this first example, we have to have u be 5 plus 3x squared, because that's the inside of the function. Well, du would equal 6x dx. But our leftover is 2x dx, so that's a problem. If you're ever off by a constant, you can just multiply by both sides by some factor. So, and I said off by a constant. I should say off by, the coefficient is off, not a constant. So we can multiply both sides by 1/3. So we'll now have 1/3 du would equal 2x dx. Well, now this back part is going to be a 1/3 du, and this part will be the u raised to the third. So we'll have u to the third times 1/3 du. Any constants you can pull out front. And I would suggest in the future, when you have like a 1/3 du, just automatically put that in front of the integral. I didn't in this first example we've seen, just so you can see where it goes and then it gets pulled out front. But I would say in the future, just put it right out front. So we'll have u to the fourth. We've got to divide out front by 4, which is like multiplying by 1/4. So a fourth times a third gives us a 12th. Then we got the plus c on the end. So for our final answer, we got the 1/12, 5 plus 3x squared to the fourth plus c. Here, our function inside the function is the 6x squared plus 1. So du equals 12x dx. We're off by a factor. We got to multiply both sides by 2 to get it to match up with our leftover stuff. So we'll have 2 du equals 24x dx. So we'll stick the 2 out front. We'll have our du at the end. And then our u is just going to be raised to the 1/2 now because of the square root. So we'll have u to the 3/2 when we go up 1. Dividing by 3/2 is the same as multiplying by 2/3. So 2/3 times 2 will give us 4/3 out front. Don't forget your plus c. And to finish off, we'll just fill back in for u. If you wanted to check, take the derivative, see if it matches with the original thing that was in the integral. All right, our last one. Sometimes when you have division, it's helpful to rewrite it as multiplication. So that's just a technique that I think can make it easier to see things. You don't have to do it. So our function inside the function would be what's inside the square root in the bottom. So we'll let u equal x to the fourth plus 2x, meaning du would be 4x cubed plus 2 with the dx on the end. Well, our leftover, this stuff here, is 2x cubed plus 1. So we've got to multiply everything by a half. So multiplying everything by a half, that would give us 2x cubed plus 1 dx. And that's going to end up going here. Well, then the integral is now going to be 1 over square root of u. We'll have the 1/2 out front and the du at the end. So we're going to have 1/2 the integral of u to the negative 1/2 du. Our exponent goes up 1, so we'll have u to the positive 1/2. Well, if we divide a 1/2 by a 1/2, that's just going to give us 1. So we'll have u to the half. And don't forget your plus c. And then we'll put our u back in. We have x to the fourth plus 2x. There's a plus here. Raised to the 1/2 plus c. Just want to check, make sure I put my exponent on that one. All right, so that's it for u substitutions. You got the homework problems to do. Any questions, post them right to the content discussion board.